Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about going through the workflow of a hull form that you've generated in Orca3D through to a seakeeping analysis in the ProteusDS ShipMo3D toolset. So why you might want to do this is if you are looking at parametric studies or exploring different variations in the hull form and in Orca3D and Rhino, and then taking that design and going through the process of evaluating like what's happening, what's the ship motion performance like. So I'm going to go to the Orca3D menu in Rhino, and what I've put together already is a variation of the 50-meter generic yacht parameters that we've been using in our publicly available sample projects. The 50-meter generic yacht has a beam of 9 meters and a metacentric height of about 0.9 meters, that kind of thing. Displacements around 560 tons, that sort of thing. So I've already done a bit of playing with this to get something that's kind of similar. Now the difference here is there's a little bulb on the other project that we have. This one I kind of wanted to highlight how what's really fun about the hull assistant in Orca3D is that you can go through and completely change what the form factor looks like. And particularly at the bow, you can go to, like, for example, a vertical bow, or give it some rake, like a conventional bow. And there's tons of options for exploring different bow bulb shapes. But we're not doing that. We're just going to do a conventional bow today. Taking a preview of the hydrostatics, you see we're at 552 tons. That's pretty darn close to roughly the same. I do like to try to keep to keep for an apples to apples comparison. I want to try to keep the displacement kind of similar. I've loaded it here. You'll note that it's offset here. We'll just go shift origin, shifting the origin to 50, 0, 0, and we're doing that, if you recall, because we want to have the reference frame at the aft of the vessel here. So yeah, otherwise the form factor is not really exactly the same as the generic yacht. I mean, it's pretty close. I wasn't trying to get it exactly the same. I just wanted to kind of demonstrate the workflow here. Okay, so we are going to create the port side. Okay, and we need to make a mesh from this, so I will go here and go quad remesh. I want to do something a little bit faster, so I'm just going to put in 500. We'll do preview of what the mesh looks like. Here we go. Sometimes I like to keep them overlapping just to kind of see how faithfully it seems to be representing the mesh of that NURB surface. So I'm going to hide that input object, and then we don't want to keep that. We just want to use the numerical mesh as input here. So that's I think that's pretty good. Pretty good balance. Make sure you do delete input objects, and then you don't have to delete the NURB surface underneath. So there's our mesh, and now what we're going to do is save this as, and what I want to do is, I've already got a named file here. We'll save over that generic yacht 50-meter conventional bow. Go save, and then go OK. Okay, and for now we're done with Orca3D and Rhino, and now let's show you how to bring that into the ProteusDS ShipMo3D toolset. So make a brand new project. First thing we'll do is we'll pick the location here. I'm going to pick this folder on my desktop, the generic 50-meter conventional bow. And here we have the particulars for the project. You can make edits to these as you go through. I think we're aiming for a draft similar to the existing project, 2.4 meters. We'll check all these values. I don't want to mess around with rudders and propellers. We're just going to do a basic seakeeping analysis here, so we'll set all those to 0. First step, we go to add new data, panel hull. Panel hull is how we're bringing this information, the hull form information, into the ShipMo3D toolset. So we switch this hull geometry input option here to wavefront OBJ. And the only thing we really need to do here is pick the file. So that's the file that we generated in Orca3D. And we click OK, and we go run. Everything's looking good. We'll just take a quick peek at it. I really like to look at ship parts. Oh, something doesn't quite look right here. Oh yeah, you know what it was? So the yellow part's the wet hull. That's really high up on the hull. Obviously, that doesn't look right. I know what I did wrong. I forgot to offset. So we have the displacement already in here. So there's two things you can do here. You can just delete it and remesh it and stuff like that. You could move it up from the up the mesh and directly in here. But what I'll do is we'll show you. If we go back to hull design, hull assistant, ship assistant, and we have generic yacht saved here. Yeah, this is the draft. You can have it at 2.4 for doing the preview of the hydrostatics, but for importing the mesh, and then later we're going to be messing with and adjusting the displacement when we're doing the hydrodynamics analysis. We don't want to be having to correct it as we go through there. So, the origin's gone back there, so we'll just put it 50, 0, 0. There we go. Create porthole. Quad remesh. Looking good. We'll save over that file that we already had there. So hang on, just to confirm, see how it's sitting right on the plane there. That's what we want, because then we're going to manually set the displacement when we get into the ShipMo3D toolset. So we'll go save as, save this file here. So this kind of gives you a good reason to make sure you just check visually that everything's looking good right off the bat before you spend a bunch of time doing the hydrodynamics calculations. So this file name hasn't changed. We're still loading the same file, but we saved over it. So I'll run that again, plot the hull. And again, I really like the ship parts color option here. It shows the wet hull. Okay, that looks way more sensible. So note there's automatic mesh refinement along the waterline. That helps a lot with water quality. I know that might be a little bit confusing if you were expecting something different. So here, like we're going to leave it at this, but say you put it at 3.5 for whatever reason, you want to look at a different displacement. You run it, and you'll see how you've got quite a bit different wetted area of the hull there. So we'll go back to 2.4 here. We'll run it. Another thing that's good to check is just verify the displacement. That's 545 tons. That's pretty darn close to what we were looking at. The main thing is to make sure it's not off by an order of magnitude or something like that. Other checks here, metacentric height, 1.1. That's maybe a tiny bit higher than 0.9, but I mean, you can adjust this by moving the VCG a little bit. Okay, we're on to the next step of adding a lid. So we go add new data and the lid. What the heck is a lid? Well, the lid is a numerical structure that we use to increase the quality of the hydrodynamics calculations. So we're importing the wet hull we already generated 99% of the time. I leave the defaults, leave wet hull waterline. For monohulls, this should work great. We'll go plot panel lid, and there's our pink lid inside the area here. So all that this is doing is a numerical structure to suppress any wave parameters that appear inside the hull through the calculation of the wave radiation and diffraction effects. It just takes a second, and it's well worth at significantly increasing the quality of the calculations. And that's it. It's the default settings I find work pretty well. So the next step is going to add new data, and we want to go to the rad diff application here. This is the main application for calculating the wave radiation and diffraction effects. So first we pick wet panel hull, and these are the outputs from the previous project. So we'll just pick what's in the folder there. And where's our lid? There's our lid. I never find it necessary really to change many of these default settings. This is just the labeling for output of the data for plotting in raddiff. This is changing the integration source parameters. I mean, it works fine. I haven't found any need to change these values. The first thing that you need to do is determine the encounter frequencies you want to use. ShipMo3D, the ShipMo3D toolset will make a guess based on monohull and the ship length that you've got here. I find for monohulls tends to be pretty conservative, so you can just leave this and you're on your way. Normally, I would recommend you calculate these first just to make sure that everything looks copacetic. For a lot of monohulls, usually there aren't any issues. But because if there are issues, you might want to remesh your hull, and it'll just be a little bit quicker than including the diffraction calculations. But what we're going to do is just do a 12 knot case, and we'll leave the rest of these defaults. This is the number of wave relative headings around the hull, and this is the number of frequencies. This covers quite a large range of ocean wave frequencies that you might find. So we'll leave it at that, and we'll save it and run these results here. So we'll let this run. This will take a little bit of time. It depends on how long it takes. Will depend on the number of panels that you have, but we used a pretty coarse mesh, so it shouldn't take too long to do. Okay, some time has passed. The radiation and diffraction calculations are done. This goes pretty quick. For monohulls, typically you don't need a high resolution of spacing. And if we look at the results, it's always a good idea to look at the radiation and diffraction values. For monohulls, there's one sort of main peak, and you want to make sure you have enough frequencies that things are kind of tailing off and sort of not converging but flattening out a little bit. Even still, you might justify using a little bit shorter of a frequency range. But my main goal was to highlight that the values that the ShipMo3D toolset are guessing that you might need are usually tend to be pretty conservative and work pretty well. So these also look really nice and smooth. That's great. And now we can move on to the next stage of constructing the ship model. So go add new data, build ship. We'll pick the hull radiation and diffraction name. Now this is the output from build ship of the constructed ship model. Sorry, this is the output from the radiation and diffraction analysis that we just completed. Optionally, you can add a dry hull. This would be important if you wanted to do a time domain analysis with a bit of nonlinear options, but this is just yet another output from panel hull. One of the main things you really need to do is provide the radii of gyration. So this is, of course, an expression of the rotational inertia of the vessel. For monohulls, there's lots of rules of thumb out there. If you don't have any information to go on at all, it's very common to see things like a quarter of the length for pitch and yaw. So in this case, we're working on the 50-meter vessel. So we're going to be looking at a value of roughly 12.5 for those two. For roll, typically it's something like 0.37 or 0.35 to 0.37 of the beam value. So for a 9-meter beam, we'd be looking at something like 3 1/3 meters. Obviously, you need to use your judgment. It's better if you get more information down the road. You can refine these numbers and see how things change. These so-called hull retardation functions are helping you map this is for time domain seakeeping analysis and maneuvering. These help you map the frequency variation in the added mass effects. For monohulls, I think these are pretty good. So we'll run this right now before doing anything else. Oh dear. Oops. Let's see here. What's the error? It says that we have. Oh, I know what I did wrong. Look, I wasn't paying attention, and I accidentally loaded a different radiation and diffraction file name. So when you're jumping between projects, it will remember the last file path you're using. So what it's saying is, hey, I noticed the radiation and diffraction database file you have is tagged with a vessel length of 30 meters and a draft at midship at 1.5 meters, but you say here you have 50 meters and 2.4 meters baseline. So yeah, I just wasn't paying close enough attention. So what I want is the radiation and diffraction values under my 50-meter vessel. Here we go there, and oh, I notice here with the file path, it's pointing to the wrong one because I was jumping between projects. So yeah, we want the generic yacht, dry panel hull here. That's looking better. Let's try running that again. Okay, great, no errors. I'm sure you can understand with these, with a lot of data around, you don't want to get mixing up the wrong ship motion hydrodynamics and files when you're working on these complex projects. So we were just looking, we're going to check the so-called retardation or kernel functions. So we go plot retard, and the retardation functions all attenuate. They sort of have this oscillation. They nicely attenuate to a nice flat value. That's exactly what you want to see. So we don't even need to make any changes here. I think it's always really good in early concept design. You want to be looking at, what does the hull shape do? What does the change in vertical center of gravity do? That's great, and you get an idea of what a bare hull is going to look like. Down the road, you can start adding. Here is where you add things like bilge keels, fin stabilizers, slosh tanks, U-tube tanks, and stuff like that. But we don't need to do that for a first pass. So you can plot the ship here in build ship. Now, this is where you would see a visualization of any appendages that you were adding and things like that. And of course, we're not doing that right now. We're just going to go to do the seakeeping analysis. So now the next thing you can do to get an idea of motions and waves is you go add new data, and we'll go to Seakeep random. Now the so-called random is just, you're looking at a spectrum. There's multiple waves in a regular sea state, if you will, not just a single sinusoidal wave. So we'll go ship motion for database file name. Now this is the output from build ship here. So we'll click on that. And if you recall, we just picked that we were going to do 12 knot speed. If you wanted to do a wider range of speeds, I would recommend you go, make sure you incorporate that into your radiation to diffraction analysis. We'll keep the seam spread of wave directions and frequencies. Here we pick the wave spectrum we want to look at. Now, Brett Schneider, also known as Pearson Moskowitz, is sort of open ocean, fully developed sea state condition. Nothing wrong with that. I kind of like the flexibility that the John Swap spectrum gives you. It's sort of more representative of a coastal developing sea, but the flexibility you get is sort of how peaky the sea state is. You can adjust this if you want to. Yeah, let's just pick some sort of moderate sea state, 2 meter, 10 seconds, nothing too crazy. You can run it right away and get motions of the center of gravity. It's always nice to check motions at different locations. So that's what these so-called seakeeping positions will help us with. You pick the station. For our default 20 station vessel, right at midships, we'll have a station of 10. Remember, we had a 9 meter beam. Maybe we want to check motion sort of at the beam, maximum beam, so something like 4.5. And then Z above baseline, maybe we want moderate spacing above the baseline, something like 4 meters. And we'll just click OK, and you can keep adding more of these positions and label them however you like. Anyway, let's run it. And it's run through a whole slew of speeds, relative directions, all these different wave frequencies are incorporated. And then we go to plot motion RMS. So here's the relative sea direction for surge, sway, heave, roll, pitch, and yaw. We have the relative direction along here. So, if you're looking at this, what does this intuitively mean? Well, 90 degrees is going to be a beam sea. And of course, we don't really see much going on in surge in a beam sea, but we do see maximum roll as expected in a beam sea. So we're getting all kinds of really detailed information about the ship characteristic motions at the center of gravity. Now this is at 0 speed, so we can pick 12 knots and see the difference here of how things are changing. And if we go back to Seakeep random, and go view output. Now this is just a text file, so you don't have to look at this in the interface here, but you've got all kinds of information here about the motions at CG for the different speeds, and then the table of values for the longitudinal lateral vertical acceleration at the seakeeping position that we selected as well. And it goes on with more information. So the main goal here was to show you a workflow of working with what a hull might look like in a sort of commercially available tool like Orca 3D and Rhino through to a seakeeping analysis. and to get some insight as to how the performance at sea would be like. Thanks for watching.